Today I am going to discuss the application of the partial differential equations, and I will derive the one-dimensional wave equation. So now consider an elastic string of size L which is fixed at point O and then stretched to the point B. So let us consider this one as the elastic string of length L which is deflected from this point O at time t equal to 0. So suppose that the string is at point P after some time t. So now the tension at this point of the string, so this is your T1, say this is the point P which has an angle alpha. Now suppose that this is your tension at point P and it is your T1, and tension at some point Q, say the tension at this point is T2 and its angle with the horizontal line is beta. Now suppose that this point is your x and this is your x plus delta x. So that means this is your delta x. Now let the deflection at this point P, let us assume that the deflection at this point P is your yxt, and then the deflection at this point will be yx of x plus delta x of t plus delta t. Now so consider an elastic string of length L. So consider an elastic string of length L which is fixed or which is stretched to the point B. So suppose that it is straight to the point B. Okay, let after deflection at t equal to 0, the string is at point P where your tension of the string is T1, and at Q your tension of the string is say T2. Now suppose that the tension of the string at this point Q is T2 and the tension at this point P is T1, and let us assume that this T1 makes an angle alpha with the x-axis, and here let us suppose that T2 makes an angle beta with the x-axis. So now to derive the equation of this one-dimensional wave equation, let us assume the following. Let us have the following assumption. So the first assumption is that we assume that the mass, the string is homogeneous. Let us assume that the string is homogeneous. That means mass per unit length of the string is fixed. So let us assume that the mass per unit length of the string is fixed. Second point, this is our first assumption. Then let us assume that a string is elastic. Let us assume that this string is elastic. That means it does not produce any resistance in bending. That means you can bend the string, and if we can bend the string, then we can stretch it to the point B. So let us assume that the string is elastic. Then the third point, suppose that the tension of the string are very large. String tension of the string is very large. Why we are assuming this tension very large? We are assuming the tension very large so that we can neglect the force due to weight of the string. We are assuming that the tensions at P and Q are very large so that we can neglect the weight of the string. And fourth point, the string moves transversely so that the deflection y and we are assuming that the string moves transversely so that the deflection y and del y upon del x, that means the slope, are small, and so that we can neglect their higher powers. So to derive the one-dimensional wave equation, we have the following assumption. The first assumption is that the string is homogeneous. That means mass per unit length of the string is fixed or constant. Then let us assume that the string is elastic so that we can bend it. Then we are assuming that the tension of the string is very large. Now, if the tension of the string is very large, then we can neglect the weight of the string. Then finally, our fourth assumption is that the string transverse or moves transversely so that your deflection y and this slope del y upon del x can be, their higher power can be neglected. So that means the deflection y and the slope del y upon del x is small. So we have these four assumptions. Now taking in mind these assumptions, the mass of the string, the mass of the small arc. Now as you can see that this PQ is very small, so we can mass of the element PQ is, now the mass of the element PQ will be m into delta x, because here you can see that the arc PQ is approximately a straight line, so we can assume its length as delta x, although it is not delta x, but as we are assuming that it is almost a straight line, so the mass of the string is delta x. So the length of the PQ is delta x. Hence, the mass of the small element PQ Now the mass of this will be your m times its length. So this will be your m times delta x. Okay. Now let us, as we, this was your T1. Okay. Now as the string moves transversely, so that means there is no horizontal force. So as the string moves transversely, so there is no horizontal force. That means the horizontal component of this tension T2 will be T2 cos beta, and the horizontal component of this T1 will be your T1 cos alpha. So these two will be equal and they will be constant, say T. So these horizontal tension, the horizontal component of these tension will be, now here you can see that the horizontal component will be T1 cos alpha, here the horizontal component will be T2 cos beta, and as the string moves transversely, so that means this horizontal component of the tension will be constant, say this is your T. So we are assuming it as T. Now again, the vertical component of T1 and T2 is, now see the vertical component of T1. Now the vertical component of T1 will be, here you can see that its vertical component will be in this direction. So for in this direction, the vertical component of T1 will be minus T1 sin alpha, and here your vertical component will be T2 cos beta. So this is your vertical component of T1 and T2 respectively. So this is your the vertical component of T1 and T2. Now due to the Newton's second law of motion, by Newton second law of motion, which is your force equal to mass into acceleration. So from here we can see that now the force at this point in the particular direction is equal to T2 cos beta minus T1 sin alpha. Now the mass of the string was, for the length PQ was m into delta x. Now acceleration at some point is equal to del 2 y upon del T2. So this will be your acceleration. So now here we can change T2 equal to T upon cos beta and T1 equal to T upon cos alpha. So from here we will have T2 can be taken as T upon cos beta. So this is your T upon, I think this is T2 will be your T upon cos beta. This is your not cos beta, this is your sin beta, because we are dealing with the vertical component. So this is your sin beta. Now this will be into sin beta minus T1. Now the value of T1 is T upon cos alpha into sin alpha, and in the right hand side we will have m delta x into del 2 y upon del T2. So from here we can write it as sin, now this sin beta upon cos beta will be your tan beta minus sin alpha upon cos alpha will be your tan alpha, and let us take this delta x here, then in the right hand side we will have m upon t into del 2 y upon del T2. Now here your tan beta and tan alpha are the slopes. Now tan beta will be the slope at the point Q. So this will be your del 2 y upon del x2 del y upon del x at the point Q, that means at x plus delta x, and your tan alpha will be the slope at point P. So this will be your del y upon del x at your x. Here tan beta and tan alpha are the slopes at Q and P. So now we can remove the figure. Therefore, if you put this value here, then therefore del y upon tan beta is this one at x plus delta x minus del y upon del x at x divided by delta x. Then this is equal to m upon t del 2y upon del t2. Now if we take delta x tends to 0, that means when your q tends towards the p, then this limit delta x tends to 0, del y upon del x at x plus delta x minus del y upon del x at x divided by delta x is equal to m upon t del 2y upon del t2. This is free from your delta x. Hence, now you can see that this is the definition of the derivative, f of x plus h minus f of x divided by h. Limit h tends to 0, f of x plus h comma y, then minus f of x comma y divided by some h. This is your derivative of f with respect to x. Now using this condition, this is the double. Now we have one derivative here, then this is again your derivative with respect to x, so this will be your del 2y upon del x2, and in the right hand side we have m upon t del 2y upon del t2. So from here our del 2y upon del t2 equal to t upon m del 2y upon del x2. If you now here your tension is positive, your m is positive, that means t upon m is positive, as both t and m are positive. So we can write, so t upon m can be written as c square. Therefore your del 2y upon del t2 equal to c square del 2y upon del x2. So this is known as your equation of one-dimensional wave equation. So this is the equation of one-dimensional wave equation, and similarly we can derive the also two-dimensional wave equation is, now the two-dimensional wave equation is del 2y upon del t2 equal to c square del 2y upon del x2 plus, say this is your u. If you take u here, then this will be delta u upon del x2 plus delta u upon del y2. So this is your two-dimensional, this is the equation of the two-dimensional wave equation. So here we have the one-dimensional wave equation as del 2y upon del t2 equal to c square del 2y upon del x2, and this is your two-dimensional wave equation. Now in the next lecture I will discuss its solution with